Welcome to the next video in the Combinatorics series. We're talking about combinatorial arguments, and this video is focused on words and subsets. So to start with, really the place to start with is the idea of an alphabet. Now, an alphabet is really just any set, although we're primarily interested in the finite sets. So to give an example, let's go ahead and take an example set S, which is 0, 1, 2. So we'll take that to be the alphabet. Now we can define a word as any finite sequence of elements in the alphabet. So if we write S star as the set of all words, then we can list several of the elements in this set by systematically listing all of the words with length 0. Well, there's just one. I'm going to write that as epsilon. So epsilon is just basically going to be my symbol for the empty word. It's basically a similar concept as the empty set. It's a word with no elements in it. It has length 0. Now, we can carry on to enumerate all of the words with length 1. Well, that's really just a repetition of the alphabet. Next, we can write down all of the words with length 2. And it's worth doing this in a systematic way. And so I'm first going to take the first character of the word and fix it at a first element. Here, a natural choice of a first element from the alphabet is the number 0. So I'm going to start by fixing the first character to be 0, and then I'm going to run through all possible choices of the second character. So that would be 0, 0, 0, 1, 0, 2, and that's everything. Where I've fixed the first character to be 0, next I can enumerate all of the possibilities where the first character is a 1. So again, I'm going to basically do the same thing. I'm going to run through all possibilities for the second character. So that's going to get me 1, 0, 1, 1, 1, 2. And then I, again, increment that 1 up to a 2 and enumerate all of the possibilities that start with a 2. So that would be 2, 0, 2, 1, 2, 2. And that gets us all of the length 2 words. We can basically repeat this to get all of the length 3 words. I won't do all of them, but we can start with 0. And then we will run through all of the length 2 words. So 0, 0 goes there. Now I'm still fixing the first character as a 0. So what comes next is 0, 1, right? The next length 2 word, basically in the previous enumeration. And then we would get 0, 0, 2, 0, 1, 0. And so on, right? You can basically see that it's exactly the same system as I used with the length 2 words, but I'm fixing the very first character in each one of them to be 0. Once we've exhausted all those possibilities, basically just run back through all of the length 2 words, but again, fixing the first character as 0, then we increment that 0, right? We then take the first character to be 1, and again run through all of the length 2 words. So we get 0, 0, 1, 0, 1, 1, 0, 2, 1, 1, 0, and so on. And proceeding likewise, right, the next one would be a 2. We do similarly, and you can sort of generalize this process to length 4 and 5 and so on. And in that fashion, generate all of the words. Now, we can see that if we fix the length of a given word at k, right? So k will be a fixed length of the words that we consider. and we want to count up all of the words of length k, then the product principle from an earlier video makes it quite trivial, right? We can kind of diagram it in the following way. So suppose that, in this case, we're taking n to be equal to 3. That's the size of the alphabet. So n is the size of the alphabet. K, let's just fix at 2, just for demonstration purposes. And we can diagram the way that we're counting this using the product principle by writing a couple of placeholders for the 2 coordinates of this length 2 word, and say that this coordinate can be filled with any of 3 options, and this coordinate can also be filled with any of 3 options, right? One for each of the characters in the language, and the product property tells us that, or the product principle tells us that the total number of such objects is 3 times 3, which is 9. And in general, if you have an alphabet of size n for any n, and you fix the length of the word at k, then n to the k counts all of the words of length k taken from this alphabet. Now, another interesting thing, which I've started to diagram up here, is that it's worth noticing that a sequence is basically the same thing as a map from the indices to the set. So, to illustrate what I mean, take this particular sequence, which is 102. What you can view this as is it is effectively the same thing as mapping index 0, right? We're going to imagine that index 0 is, corresponds to the first element in the sequence. Index 0 is mapped to 1. Index 1 is mapped to 0 because, the next coordinate is a 0. So this is index 1, and we're mapping it to 0. And finally, index 2 is mapped to 2. So that, in this sense, every sequence is some function from the index set to the alphabet. And vice versa also, right? Every function like that corresponds to some sequence. So that there is this one-to-one correspondence between the words of length k and the functions with domain bracket k and range equal to s, the alphabet. So therefore, if you count one, it's the same thing as counting the other, basically. It's where this is going. So, by the principle that we established that if you fix the length at k, there are n to the k words, by the same principle, the number of functions with a domain of size k and a range of size, the size of s, whatever the size of the alphabet is also n to the k, right? So basically, by counting the words, and there's a one-to-one correspondence between the words and functions like this, we've also counted the set of all possible functions that are like that. So anyway, next let's discuss simple words. So a simple word is defined as a word for which every letter occurring in the word is distinct from every other letter occurring in the word. A simpler way to say that is it's a word with no repetitions, right? No characters in the word are repeated. Now, this is basically the same thing as like a permutation, right? I've indicated here all of the simple words. Now, epsilon, the empty word, is technically a simple word because it doesn't have any repetitions. It doesn't have anything at all, so of course it has no repetitions. We're often not really interested in that when we're talking about permutations, but it technically counts. Anyway, every length 1 word has no space for repetitions, so those are all simple. But when we get to the length 2, I finally have some things that don't count as simple, like 0, 0. But 0, 1, no repetitions, so it's simple, and so on. If we want to count all of the simple words, we can use a system very similar to the one that we used for counting all possible words. The only difference is that, well, okay, so what is the same is that the first coordinate can be filled with any of 3 possibilities, but having chosen that possibility, the next coordinate only has 2 possibilities, so this is the way to count all simple words. It is effectively, we'll give a formula for it in a minute, but in any case, in this situation, it is clear that the number of ways of counting all possible simple words is 3 times 2. Okay, so the foregoing considerations make it clear that we have at least a little bit of use for this notation of the falling factorial. So to introduce it, let's imagine that now, just for demonstration purposes, we have an alphabet of size 7. So we're going to set n equal to 7. And we are looking for all of the words of length k, which we set equal to 3. We diagram it like this and say that the number of simple words in that setting is 7 times 6 times 5. And so to help us to write that efficiently, we'll call that 7 sub parenthesis 3. So what that means is that you start at 7 and you take 3 factors in total descending, the subscript. The fact that that is a subscript means that we will use descending factors. And that is the number of simple words when the alphabet has size n and we fix the length of the word at 3. As I have in the slide here, there's also this pi notation, right? That's a capital pi. So that's the somewhat more professional mathematician notation for the same thing. And I've given another example just to demonstrate. So next, we have the rising factorial, and that is written with a superscript, right? So 7 to the parenthesis 3. And we haven't yet seen anything that counts, although, I mean, we could, but there's really nothing where that comes up naturally just yet. But we, introduce the notation anyway. And so it basically just means that because when we write it as a superscript, it means that the factors are incrementing rather than decrementing. So 7 to the parenthesis 3 means start at 7, increment the factors, and give me 3 of them in total. And again, it has a pi notation, and in the slide I've written another example. Now, in the, what I now have on the slide, I'm just showing a few things that are somewhat familiar, which could be written in the falling or the rising factorial notation. And this is not genuinely interesting. I'm only displaying it to show you a few just very basic introductory exercises in using the rising and the falling factorial. So, to demonstrate, n sub parenthesis n, right, n falling factorial n. Well, that means you start at n and descend n times, so you get n, n minus 1, and so on. This terminates at 1 because, if you're starting at n and you descend n times, you end the whole process at 1. Well, that's just the same thing as n factorial. So that's a, cute little application, I suppose. And we could do it in reverse, right? So if you started at 1 and you increment n times, that's the rising factorial, and that also gets you the same thing, n factorial. Similarly, somewhat, the binomial function n choose k can be written according to this formula where, it's not too hard to prove that this actually amounts to the same thing that the usual formula amounts to, just by canceling a bunch of terms. It should be somewhat obvious from from a background in discrete mathematics. But if it's not, then just write it all out, cancel factors. It should become apparent. So anyway, there are just a few demonstrations using these rising and falling factorials. So what I now want to do is I want to present subsets as certain kinds of functions. So let me explain what I mean by that. Now, to begin with, I'm going to be focused primarily on sets that are of the form bracket K. Bracket K is notation which just means the elements from 0 to k minus 1. So there are k elements in that set. And the idea here is that this is going to be my canonical set of k elements. If you had any other set of k elements, then in effect, whatever I do to this set, you could also do to that set. But in any case, let's just, for now, let's just think about this particular set. And for illustration purposes, I'm going to take k equal to 5. So bracket k is going to be the numbers ranging from 0 to 4. And I want to take a subset, call it S, and it's going to have the elements 1, 3, 4. So this is indeed, S is indeed a subset of bracket 5, right? And what I want to do is I want to present S as basically the same thing as a certain function. Namely, it is the function which is going to take an element of S, an element of bracket K, and map it to 0 or 1 depending on whether the element was included in S. Because that's always a yes-no, right? It either was included in S or it wasn't. So for instance, we map 0 to 0 because 0 here was not, you kind of read that output value 0 as a not in. So because the element 0 was not in S, then we map it to 0. Because 1 is in S, then we map 1 to 1, right? So this is like an element of S, and this is like a yes-no, or an in-out, basically. So, going likewise, because 2 is not in S, we map it to 0. Because 3 is in, we map it to 1. Because 4 is in, we map it to 1. So that in effect, subsets are basically the same as functions like this. And when I say a function like this, well, what I mean is a function with domain bracket K, right? Domain is the set in question. And the range is the set 0, 1. 0 encoding no, or not in, and 1 encoding yes. A function that is like this, we often write as chi sub s, as I have here in the slide, and it is called the characteristic function for the subset S. One of the upshots of talking about this at this particular moment is that we have already seen just a moment ago that the number of words with an alphabet of size n and length k, there are n to the k of those functions, right? Well, we can now use that, right? That basically gives us a formula for counting a set of functions. So we can apply that here because we have a set of functions. So if we apply that here, where our functions have domain bracket k, which has size k, and codomain, range 0, 1, which is always size 2, what we can infer from that is that the number of all characteristic functions is 2 to the k, right? So we've now counted all of those functions, but based on what we just talked about, there's a one-to-one correspondence between the set of characteristic functions and the set of subsets. So effectively what this establishes is that the number of subsets is 2 to the k, just the same as the number of functions. So, right, that's kind of the upshot. I mean, many of the steps along the way were each kind of interesting in their own right, but there's also the big upshot, which is a semi-famous fact from combinatorics, one that you really want to notice and carry with you into future subjects, is that the number of subsets of a set of size k